So welcome to the next virtual simulation lab seminar. Today we have Oda Dahlen from the Department of Chemistry. She's going to talk about SymPy, which is symbolic manipulation of mathematical expressions.
Okay, so thanks for the introduction, Brian. So my presentation will be an introduction to SymPy. Can you hear me in the back? Yeah? Okay. The aim of this presentation is that you, without any experience with Python, can go to your office and actually use SymPy. You do not need to know any Python to be able to understand this presentation. So what is SymPy? Well, it's a Python library for symbolic mathematics. I started working with SymPy because I was teaching it, and I hadn't really used it before. But then when I got to know it, I understood that, okay, this can actually be helpful to me in my PhD, because it has a lot of, can solve matrices. We will go into that in a short while, but I understood that this can actually be very useful to me. And then you can think maybe SymPy can be useful to you as well. So I want you to think about, in your job, during your PhD or your master's or whatever, have you ever encountered, for example, wanting to expand or simplify an algebraic expression like Brian just described? Have you been struggling with unit conversion? Have you had a very tricky differential equation? Maybe matrix problems? Maybe just don't really have a very nice way of calculating products, sums, limits, etc. Or you have been using other programs that do kind of the same thing, like Maple, Wolfram Alpha, but maybe you want to try something new and cooler. Or have you already been using Python for a while, but maybe thinking about, okay, maybe Python can do more for me, because it can, for sure. So let's just take a short look at the features of SymPy. In this link, it has listed all the features that it has. So of course, it has basic, like a calculator would have, basic arithmetic. Yeah, like we talked about, expansion. It contains many types of functions. We can do calculus, like integration, differentiation, series expansion, and matrices. We can find all kind of stuff you want to calculate from matrix. And there is a lot of stuff here. I will go through some of it, but if you are wondering, maybe I will find what I need, you can go to this page and look what it has. And actually, the development of SymPy is ongoing all the time. And every year, I think the Google School of Computer Programming also works on SymPy to expand it more every the summer school. Okay, so let's go back to the presentation. Okay, so these are just the links that you can use. If you want to have Python, if you want to use it on your computer, you need Python, and then you can install SymPy as an extra library. If you don't have Python, you need to download it from here. You need version 2.6 or later, but I would recommend you to download version 3 because that's what's going to be used in the future anyway. So you might as well learn the syntax. It's not very different from Python version 2 anyway. And then you can download SymPy from here or here. If you already have Python and you know a bit about programming, you can go here and actually just install it with a few commands on your terminal window. So these are just links for you to have if you want to start using SymPy. Okay, so you might have noticed that here in the top here it says Jupyter, which is a IPython notebook. IPython stands for Interactive Python. And normally when people use Python, they download a integrated development environment, which are called IDEs for short, which is like idle, Spider, PyCharm, and many other programs which you normally use when you're programming. Probably many of you have heard of these or other IDEs. You can also just use your default terminal on your computer, of course. But I chose to use this Jupyter notebook because it's, first of all, it's very good at displaying graphics. Oh yeah, and I have to, before I get into that, I want to show you one thing. If you don't want to download anything, you just want to use one thing in SymPy and then forget about it, then you can go to this page here, which actually has for you a live version, online version of SymPy. Here you don't need to download any packages, anything, because it has everything that you need. So here you can just write your commands and execute them. So this is like the easy version if you want to use that.
In the same way that you would do all your commands in Jupyter.
Yeah, this is like the same way as you would do in your terminal, what I will do in Jupyter, and what you would do in one of these programs. Yeah. Okay, so why I'm using this Jupyter notebook is, first of all, the graphic. I will not go into the code here now, but I will execute this code. And you can see that it prints out an integral fairly nice. And the derivative looks like this. Now here is a screenshot from my terminal, and it doesn't display it very nice. So for presentation, I mean, I understand this, but for a presentation, I think the Jupyter notebook is quite good. The other good thing about Jupyter is that you can have text and code in the same document. And I can also decide that I want to not have executed this one, so I can say clear all output. And then you see that the output disappears, and then I have to execute it again, which is quite nice because it's more interactive for you guys when I can rework this stuff. The last reason is that it offers tab completion and a better help system. And I'm sure that some of the IDEs also have a quite good, or I know that they also can have a good help system, which is a lot of the reason why people use them instead of just using their terminal. So tab completion basically means that, let's say I want to use a function or a tool from SymPy. The syntax is like this: from SymPy import, and then I need to write whatever I want to import. So let's say I want to differentiate, but I'm not really sure what the name is. And I can write, for example, di and hit tab. And then I can go down and look, okay, this is probably the differentiate. You can also just hit tab and see all the stuff that you can import. And then you can, for example, decide to import Gram-Schmidt. Now, I don't really know what Gram-Schmidt is, so I will go to the next one, and I hit GR and then tab, and then it gives me Gram-Schmidt, because I already told here that I want to import Gram-Schmidt, so it knows that it's available to me. And here I write Gram-Schmidt and I write question mark. And then it will give me some information. But I don't really understand exactly what this says, so I want more information, so I will add another question mark, and it will give me more information. So this is quite nice functions to have when working. You don't have to Google everything. Something up, Brian?
Oh, no.
No? Okay. Okay, so let's start with SymPy. So SymPy treats mathematical objects symbolically. That means that we don't represent them approximately, but exactly. So for example, if we import the square root function from math, which is not a SymPy library, and then we compute the square root of 2, we will get this, which is, of course, you know, an approximation to the square root of 2. While in SymPy, if you import the square root function, you will not get the approximation, but yeah, the actual square root of 2. So this is how SymPy works. It displays it and treats them exact. So for example, now here, if we try to find the square root of 2 times the square root of 2, we will get an approximation, while in SymPy we will of course get the exact answer. So yeah, that's quite the main object of SymPy. So let's say we add 2 fractions and we don't use any functions from SymPy, so this is just Python, and we get this. While in SymPy, I can make it like this. While in SymPy, fractions are represented by rationals. So I import this and I write rational and then 1, 2, and it's represented like this fraction. So now if I add this and this, I will get, yeah, 5 divided by 6. So this is like the point of, well, this is what it means to represent exactly. Another useful function in SymPy is pow, which just gives the power of a number. So 10, if you write 10, 0.34, you get like this. And just using normal Python, you would just get this approximation. Now, it can sometimes be annoying in SymPy that you always get the symbol, because, for example, if I import pi, we'll try to keep it here so it's easier to see. If I import pi and then I print it while just writing pi, it will, of course, just give me pi. Sometimes you might actually want to know what the numerical value of your symbol is. So the way you do that is that you can add at the end of pi either eval f with brackets. It will print out the numerical value, or you can change this with n. It's actually the same, more or less the same function. So this is a nice thing to know when working, in case you really want to know the numerical value. So let's say now that I can also decide how many decimals I want to print out by adding a number inside the brackets. And this can be done also with n. And I can print out, for example, 100 decimals. So this is good to know. Okay. In SymPy, I said that variables mathematical objects are treated as symbols, right? So in SymPy, before you do mathematical calculations, for example, write an equation as a function of x or y, you need to define the variables explicitly. The way you do that is with the function symbols. Now I import everything we use with this command. I know that it is possible to write from SymPy import star, which will import everything that SymPy has for you. But in general, I don't like to do that, because if I write from SymPy import and then I use some other library and also import with star there, I might have conflicting functions that, and I'm not sure, am I using the SymPy one or am I using the math one? So I like to define explicitly what kind of stuff you want to import. And this you would normally do this if you're writing a script, you would normally just do this in the beginning of the script.
Oh.
Sorry? Like this, yeah, okay, thank you. Yeah, so here we need to import symbols, and then the way you define them is just writing them with a comma in between, and then symbols, brackets, and here you should just have a space in between. Now they are defined as symbols and we can use them in expressions. Now actually, you don't really need to have the same letter here as you have here, or name. You could actually do like this, but it would only confuse you, because then if I write set, it actually refers to the symbol y. I don't know why you wouldn't really want to do that, but it's just good to know that it's actually not necessary that they are the same. It just depends on where you put them in the line of variables here. Okay. Now I can write, for example, this equation, and yeah. So now I can use them as symbols to make equations or expressions. Okay. So what can we now do with the expressions that we make? Well, first of all, we can differentiate and integrate. I want to show you how to do that because it's quite an important tool. Differentiate, integrate, what can it be? Okay, find it there. So now what you can do is write diff, your expression, and then the variable that you want to differentiate with respect to. Oh yeah, I didn't execute this one, so it didn't import diff. There. Okay, so it's fairly easy. You can also, instead of writing the expression inside there, you can just define the expression like this, and then write the expression inside the brackets. Yeah, it depends on what you prefer, really. We can also differentiate several times. Let's say we have x to the power of 5, and we do like this. So we have differentiated it one time. Now if I add another x, I will find the second derivative of x to the power of 5. And you can add as many x's as you want. Instead of adding a lot of x's, you can also just write x and then comma and then the number of derivative that you want to find. Like this. Yeah, so that is how you find the derivative. You can also differentiate first with regards to x and then with regards to y. like this, for example, you can do, you can do whatever you want here. Just remember to have the expression here, comma, and then the variables that you want to differentiate with respect to. Okay, are there any questions at this point? Yeah, you should be able to, I'm just going to show very simple examples now, but you should be able to differentiate. I'm not sure about a matrix. Yeah, I'm not sure. But we can check, I can look in afterwards. Then the integrate works the same way, like this. And you calculate it. Okay. Now, earlier, sorry?
It's missing a constant there, an arbitrary constant.
Oh, okay. Yeah.
No, it's okay.
Yeah, that's true, actually. Well, anyway. SymPy's fault, not mine. So earlier I showed you how to display an integral or a derivative. So actually you don't use diff and integrate to display integrals or derivatives. You actually use the two other functions that are called integral and derivative. So these will display your integral. So let's say you have like this, and with respect to x, execute this, and this. Yeah, so it displays it like this. Here you are also able to add limits for the integral. Just add another parenthesis and add the limits inside. Like this. You can also have a and b here if you want, but in order to do that, you need to define a and b as symbols, as we did with x, y, and z. Because SymPy requires that you define them as symbols before you use them as symbols. Yeah. Okay, now, it might be that for example, let's say I define this expression 1 as the derivative of x to the power of 4 with respect to x. Now I can print out this expression. It looks like this. But then I actually decided I would like to have this calculated. Then I can use a function that is called doIt. And I add this to the end of the expression, and it does it. This is where you see that Python is intuitive. So you can also do this for the integral. I can define this as expression 2. And then I can here, expression 2, do it. And it evaluates the integral. So I like this doIt function because it's funny, actually. Okay, so I will go through some more of the stuff that you can do. Substitution, which is it does exactly what it says. So if I have an expression, say p times x to the power of 2, and I can print that expression, and then I have to write expression dot substitute the value you want to substitute and what you want to substitute it with, and you get out the answer.
What if I had an equation for x and like x y plus z, since you have this defined as symbols. Would it put the y plus z in there, square form?
Yeah, I can try to do that. Like this, you mean? Yeah. So that's the substitution. Now we talked earlier about expanding and factorizing. And basically, if you have an expression like this, and you write, oh yeah, I have to, of course, import SymPy, import. This syntax you should know before starting to using SymPy, but it's basically the only thing you need to know. We have this expression, and I want to see if it's possible to expand it. It was possible. So now if I call, this means that the expression 2 is this expression. And then I can do factorize that one like this, and yeah, I get back to the original expression. So this can probably be used for a lot more complex expressions, and but I wanted to show it's not the aim of solving very difficult equations today. The aim is to show the syntax and how you use SymPy. So sum and product. Let's see. Sum, yeah. And let's say I want the sum of all integers from 1 to 10. Let's see now. Yeah. Maybe I have to. Oh yeah, I have to put this inside I guess. Oh no, I have to see what I am doing. Oh yeah, okay. Yeah, it needs to know also which variable. And it should be, okay, yeah. It's actually a bit, sometimes they have a big letter here and a small letter here, and sometimes not. And I'm not sure if that is intended. I don't think so. So yeah, this just shows the sum of this expression. And then actually there is another function that you should know about, which is just big N. And what N does is that it prints out the numerical result of your last calculation. I hope this will work now. Yeah, okay. So it will always refer to just the last thing that you printed out, the last symbolic value, so to say. Product works more or less the same way. We can also then just, it has the same syntax, like this. And here we can also print out this value with adding an underscore inside the N. Yeah. So these are just the functions that are nice to know about. Okay. Solve is a tool that will assume that your expression is equal to 0. Are there some questions now? No? Okay. Yeah, so solve we'll try to find a value for x or y or both based on the assumption that your expression is equal to 0. So let's say we have 2x minus 1, and we want to solve it with respect to x, of course. And we get a half. We can add the more complex equations. Let's say x to the power of 4. And we will get all the solutions, including the imaginary solutions. It can also solve linear systems, so a system of equation. Let's say we have one expression that is plus y, and let's say the other one, 2 times y minus x minus 5. Okay. And then solve needs to have the expressions within a square bracket. Here you could also just write the expressions, or you can define them on beforehand and write the names of them in here. That doesn't matter. And then you tell it that you want to solve this with respect to both x and y. And you get solutions for x and y. So that is quite sweet. Okay, now we'll talk a bit about matrices, and then units, and then I think that is the end of the presentation. So, matrices. Of course, SymPy has a matrix tool. And the way that you define a matrix is you need two, you actually need to have, I will show you, okay. So let's say we want 3 rows. We need to have them inside first this bracket and then the square bracket, parenthesis and then the square bracket. And then each row inside a square bracket again. But this syntax is easy to Google. I mean, you don't need to remember exactly what kind of parentheses you need. So let's say we do like this. And now, oh yeah, import the matrix first. Oh, and I also have to actually, this is something with my computer. Let's see. Oh yeah, and print out the matrix. Okay, so it will look like this. Now you can do a lot of stuff. You can, for example, access the row of the column. You can decide. Python starts counting from 0. So to access the first row, you need to write 0. It will print it out. You can access the column by this short command. Let's say we want column number 2, we need to write 1. If you have a lot of columns, you can access the last column by writing -1. This will in fact be the same because we only have 2 columns. And you can do the same with row to access the last row in the matrix. You can also delete columns easily with this command, and then you write the number of the column you want to delete. And then we can print out M and see that it actually Oh, okay.
You might have to put m comma 1.
Hmm?
Should you put m comma 1?
In there? No, I don't think so. I think. Oh, okay. Maybe I already. Oh, okay. I already emptied the matrix. I probably hit the execution button too many times. Well, I can just define it again here. And then try to delete the row. 0. No, okay.
I think you have to put m comma 0. It's just self.
Here, you mean? I don't think I did that before. Okay. Well. Anyway. We can move on. Okay, let's say we have M is this matrix. Let's say we can just have this. And then we can define N as this matrix. So then you can do whatever you want with them. You can add them. Oh, what is it that? Okay, yeah, something weird. Yeah, you can add them like this. You can multiply them. You can find the transpose with this command. You can also create a n times n identity matrix. Either you can use an existing matrix that you have and then write I, and then how big n should be. So you easily create like this. You can also have, say, a new matrix that we just call K. Then you need to tell them that it is a matrix. And then we can print out K. Yeah. But if you already have an existing matrix, you can just use I on that matrix, and it will change it to a n times n identity matrix based on the number that you give here.
Can we have symbols in the matrices? Like, can you have just like x square, x cubed, stuff like that?
I am sure that you could put symbols in the matrix. Yeah. That's what you meant, right? Yeah. Mm. Okay, transpose, identity matrix. Also, you can create a matrix that is just zeros. And if you have a matrix, finding the determinant is just by adding determinant behind. Of course, this would evaluate to 0 since I tried to find the determinant of this matrix. And also you can find, of course, eigenvalues. Now, I have this matrix here that I didn't want to write all in front of you. And now if I just write eigenvals, it should give me the eigenvalues. Yeah. These are the eigenvalues. This in front of the comma, no, in front of the column. And these are the algebraic multiplicities. Yeah, so you can basically do whatever you want with the matrix, and this is just a very brief introduction to matrices in Python. Do you have a question?
No.
No? Yeah.
I've had to do that, take determinants of large symbolic matrices.
Yeah.
So that was not nice.
Okay, so the last thing I'm gonna talk about is units. It's based on the SI units, so which has been accepted by most countries except the US. So you have to import the units from a sub. I'm going to rename units U. So this is how you rename something. You import it. I have to import this from a special part of SymPy called physics. I should write import here, sorry. And then I import units and rename it U. Because then I can write U instead of units rest of my code. I will execute this, so it imports it, and then I can write, for example, U mass. And it will give me kilograms. So this is the default mass measure or unit. I can also, I can write it here. For example, and it will give you watt. And you can also, of course, divide units to see the relationship between them if you, What's really nice with the units package is that you can, let's say that you have let's say that you want to calculate an area, and then you have given the first one in meters. So this is how you make length 1 equal to 3 meters, is to multiply it by meters. And you need to write U dot because you're getting it from here. So now if I do like this, so we have 3 meters.
If you write U dot and tab, will that give you a list of all the sort of quantities I can see the units for?
Yeah.
So if I forget, say, what the units of viscosity or something, I can go check that out.
Yeah, what you also can do actually is, I can show that here, is that you can search for a unit. So I think unit find, and then, I'm not sure if this is the exact, no, I need to check the exact, okay. Find unit, but I need to have this. And then if I'm looking for something with magnetic something, I can write what it starts with in there and get out what units are available. So that's quite useful. And also, as Brian said, you can also hit tab and see what's here.
Does it have the permittivity of free space? I always forget those units.
Maybe not. Or do you have any? Okay. Let's see. Okay, so now if I have length 2 equals to 40 millimeters. And now I can calculate the area just multiplying these two and print out the area, and it will convert to meters squared, and you don't have to think about whether you're doing it correct. And then I want to print out the value here, so I will just try to use this one. Oh no. Okay, yeah, it's not possible, but I can actually write like this, I think, yeah. So then if you are I know I had some that you sometimes mix up, and it's just like you can check that you're sure that it's not your head that's wrong. Yeah. Okay. I think that was what I wanted to show now. There is a lot of stuff, so you should go and check it out for yourself. But I hope that at least this could be an introduction so that you can feel that you maybe want to go use SymPy. So I have a test at the end. And the test is, do you feel now that you can go to your office and use SymPy? But you only have to think about it inside your head. Yeah. Okay. Thanks for your time.
So thanks, Uda. Sweeping round of applause that was. So now, is there any questions? Yes, Titus.
So, what do you think is the main advantage of this compared to more graphical things like Maple, Mathematica, or Maxima?
Yeah, I think first of all it's in Python. So since I feel feel more and more confident with Python, it's just an addition to Python. So that I don't need to learn Maple or Mathematica because I never used them, for example. So for me, it would be more natural to use SymPy since I know, yeah.
Yeah, the use of it is just like doing code. So if you're doing coding a lot, then doing the symbolic manipulation is quite straightforward. If I can remember back in the primitive days, I think it was about 2000 when I was doing symbolic manipulations. It was like building equations with the Microsoft equation editor. So that's how you like put together all your differentials and integrals and things like that. It was really pain. So
Isn't it really free, a code worker?
It's free, yeah? Yeah, that's a good point, yeah. It's of course free. And I think like, it can also be nice to use. It can also be nice to learn SymPy and then maybe gradually learn more and more programming. Yes.
I have another question. Because one of the things is, of course, solving something, symbolically. But sometimes, I mean, in other programs that I mentioned, you get an expression which looks horrible, and then there are options to simplify it. And then usually there are several types of options to simplify it, because what the computer thinks is simple is not always what I find simple. Do you have similar things here?
Yeah, there is actually a function in SymPy called simplify.
Yeah, but that's just one option, so it's just what the computer thinks is simple. You have to live with that, or...
Yeah, do you know that it's only one option?
No, not sure. No. I mean, I know it's Maxima, WX Maxima, which is also freeware. That's more graphical things. There you have several ways to simplify. So if you don't like it, then you try option number 2 to simplify, option number 3. And quite often then there is one of them that looks quite okay. Or sometimes you have to do yourself some substitution and then try again. But I wonder, how flexible it's here.
Yeah, it says here that well, there is not only the function simplify, but also, for example, factorizing. But
that kind of things,
yeah. I haven't used simplify, so I'm not sure how advanced it is. But I think they just mentioned that you can use factorizing and expand factor list. Yeah. So, but there is some different here. Collect. Here you can actually read about this. All the different stuff they have to simplify an expression. partial fraction, decomposition, trigonometric simplification. Yeah, so it's not in the simplify function, but there are different functions in SymPy that can simplify in different ways. Yeah.
Does this work with tensors?
I don't know. Okay. Any more questions?
Do you know how it handles large scale systems? For example, 100,000 times 100,000 matrix?
I think I would use Fortran then.
But sometimes it's useful.
Yeah, I'm not sure actually, but in general, Python is a bit slower at very huge calculation compared to C or Fortran.
But if
I
you,
guess.
for example, the symbolic toolbox in MATLAB, if you try to do such a thing, it will just crash your computer.
Well, I haven't really tried, but I'm not sure how powerful it is really. Yeah.
I wonder if you could run it on the HPC machines, the SymPy.
Yeah, I guess.
But then you'd have to put in the 100,000 by 100,000 matrix involved by hand. I think that would be a pain too. But you could give it a go if you really have a system and you want to try it. I'd like to hear the results.
Mm.
You said it could do differential equations and things like that.
Yeah, but I didn't really show that. But it has a function for that as well.
So it will solve it, basically, a differential equation.
Yeah. It had, let's see. Yeah, it has but I don't know exactly how to use it. But I saw an example of it, yeah. Okay.